Thank you all for coming here. I'm Giancarlo Nicolò from the University of Valencia, and I'm talking to you about scheduling. In general, I'm going to start about a brief introduction, the problem explanation, our proposal, and experiment. So, the introduction. First of all, our idea. So, in general, we want to apply a multi-agent system of our problem of energy-aware scheduling. Why? Because normally scheduling problems are tackled using some mathematical programming, constraint programming, meta heuristics, and we want to embed in this kind of problem the kind of feature that a multi-agent system has, especially reactivity and scalability. And to validate our study, we're going to investigate a real case study of plastic production by injection molding that was modeled as the model introduced to you before. So, just start with the problem. As any scheduling problem that you are aware about it, we have a set of resources called machine that model this injection molding machine. And then we have a set of different order that are our job that represent the production of different kind of plastic unit in general. And we want to optimize some objective function. Here we have different characteristics for each one of the job, and especially we have a release date, that is an hard constraint, and a due date, a soft constraint, and a penalty cost. Moreover, each job has different kind of characteristics, especially that each one of these jobs can only be processed by only one machine from a particular set of eligible one. And each one of the job has different kind of processing time and energy consumption depending on the assigned machine. Moreover, we have something that we need to take in consideration that is called the setup time. And this setup time depends especially about the machine where the job is assigned. As you can see here, we have a schedule of 3 different jobs, and in the same configuration we have 2 different kind of setup times. Moreover, these setup times is also depending about the position of the different jobs. For example, here in the same machine, as you can see, depending on the order of the 2 jobs, we will have a different kind of setup time. And both of these last features are the ones that really explode the difficulty of the problem. So our framework proposal. First of all, our initial idea and motivation to use this framework was to have this kind of analogy between each one of the machine to be represented and simulated by our agent in the system. And moreover, when you start to tackle the problem and start to understand a little bit more about it, you will start to know that another really huge difficulty of the problem is to allocate this shared job to find an optimal assignment to each one of the agents. Sorry, the pointer is a little bit moving. And okay, I will not use the pointers. And this is also an NPR problem. And you will think, okay, if I have an optimal assignation, maybe the problem can be easily solved. No, this was also demonstrated that this is another NPR problem. And so our idea in general, why I'm talking about a framework rather than talking about a system, is because the framework will be composed about different functional modules that the implementation will solve both of the sub-problem that I explained to you. And to tackle this sub-problem, we're going to use some different ideas. The first one, for the job assignation, we're going to use a space reduction strategy that will take advantage of what we call restriction over shared job. And the implementation of this kind of strategy will give us 2 different approximations. The one is called remove one machine, and the other one is assign one machine. And all of this is done by an agreement over some job property that will define the restriction. Moreover, in the single machine scheduling, each one of the agents will deploy some kind of distributed search, distributed scheduling, and both of them are used to find some local solution, at the same time take out this job property that I explained to you before. And why this is a framework? Because all of this is considered like black box, and then you will define the implementation that you can be extracted from some of the state-of-the-art approach. So here an idea of the general architecture and general workflow for a problem instance. And as you can see here, we have two different kind of agents, a supervisor agent, a worker agent, and each one of these agents is composed about different kind of module that will work, and to their communication and interaction will lead to the production of a final problem solution. And then now I'm going to show you step by step. So just to think in this way, we start with a data problem that will send to a supervisor agent that will start to understand which are the shared and non-shared job, and start to instantiate as much agent as are the machine in the problem. After that, we start with what we call the centralized solver. So this agent will create what is an initial job assignment and a local solution that will be sent to each one of the worker agent. And here an example. For example, as you can see here, on the left, we have the assignment of the shared job, and here the assignment of the non-shared job. After this, we have this distributed search from each one of the agents. We are going to do what we call the local job property and the local solution. Here as an example, each one of the agents start to create the local solution and define what are these the job that satisfy the local property. Here the formula is just to represent you, but you can find more detail in the paper. After this first step of the distribution, then the agent will start to have this agreement that is basically aiming to find this global job that will satisfy a global property. Here an example, they will start to share the information about their local job and define which one is the global job that satisfies this global property. And after that, they will start to find what are these restrictions over the shared job here. And firstly, they will start with this kind of reschedule that is mostly like the job that has this local solution has to be validated between all the ones that can schedule the same job, and this is done by what we call a reschedule. And indeed, what will happen that here, as you can see, the initial job that has this global property has been sent to all the other worker that has at the same time the possibility to schedule this job and find a kind of different variation over the multi-objective function. And from this kind of variation, we will start to create an order set of the possibility of the worker that can have this kind of variation. And indeed, depending on the number of the worker that in the next step will be present in the restriction set, you will have the two strategies that we defined at the beginning. Remove one machine and assign one machine. And to finalize the framework iteration, the supervisor agent just receive all the local solution with the set of restriction and build a global solution. So moving forward about the experimental comparison, as I introduced it to you, we have a multi-objective optimization where we take in consideration three different objectives: the total weighted tardiness, the energy consumption, and the setup time. Moreover, to make the things simpler at the computational level, we are going to do a normalized weighted function. And we have from previous work of an Italian group, we already have some problem instances that have extrapolated from real data. And the only problem in this case is that a real instance is really too big that neither a MILP approach can be feasible. And so that's why we start to do different approximation. And in general, the class of instances can be defined in different kind of class. And while the initial class has the same size, then we start to use a synthesized class where the size are more similar to real instances that we use kind of more extended time for experiment and to see some other different behavior. So in general, as I introduced to you at the beginning, we are talking about some framework. What does it mean, a framework? So that the implementation can be in a way like already existing heuristics, another optimization technique. And in this case, we want to benchmark this framework implementation that we have introduced to you before, the ROM and the OM, that can be resumed here in the right. And while taking one part of the model of same heuristic, that in this case is the genetic algorithm, we want to compare the two behavior over our experiment. So here you have some results. Okay. As you can see here, when we have really small instances that are not even comparable, just 20% of the size of a real case, the MILP approach is completely outstanding with respect to the other approximation. While when we have results that are more similar to real case, this is 50%, MILP is not even really kind of valuable solution that is producing. While when we have a size of the same size, the MIP, it's not even possible to load the problem in the memory. And so this is just to let you know when we have the MIP comparison that here this is energy aware, because even a small improvement, it's really important, because we are talking about one of the most energy expensive industry in the manufacturing field. And these are the percentage variation about the MILP approach. And moreover, because this is a multi-objective optimization, but we use a normalized scalar function, we want to use different kind of P. The first one was done after a long study with the decision maker. And then we had where the total weighted tardiness was the one prioritizing. And then we start to use some different combination to express different case scenario. But in each one of these cases, we have always that the approach called assign one machine is the one that is having the best result. And then what happened? That when we created the instance that has really the same size of a real case scenario, we want to understand if for the short amount of time, the behavior will be also the same when we have a bigger amount of time. And here, as you can see, it's not the case. So if normally the assign one machine is the one that is winning, the remove one machine then will have a better outcome. And even if here it seems like the scale and so on, as you can see here, another interesting insight is that normally we have this heuristic that as much time we leave to them, they will always improve the results, hypothetically. But here, after reaching this asymptotic behavior, we can think that the different model that we had, this collaborative reasoning of the framework, is the one that really makes the difference and permit us to reach in a same amount of time this speed up improvement. And so some conclusion in general, we have done this design of a multi-agent framework for energy aware scheduling. We developed this to have implementation, and we have also tried to extend the study over different kind of Ps and have this kind of analogy between the asymptotic behavior of normal heuristic with this framework that use some kind of reasoning, distributed reasoning between agents. And to move on, future work. This is just an idea of an initial implementation of this framework. Maybe we can have more changing to see how this can improve the results. And moreover, now we just use a normalized weighted function, while we can use different multi-objective criteria, Pareto front, epsilon constraint, and so on, lexicographic. Moreover, some other work that we are pursuing at the moment are related about dynamic scheduling and rescheduling, and even have a different energy model that take in consideration like different peak of energy, different mode, and so on. So that's all. Thank you for your attention.
So any questions or comments? Hannah?
You were talking about rescheduling, dynamic scheduling, but I'm not sure how these kind of things are reflected in experiments. Am I missing something? Can we see something? How, let's say, these kind of things change the work?
So in general, we have also proposed another work about this dynamic scheduling case. In our, mostly it's about rescheduling. So you have to take in consideration some incidents that can appear in your scenario. And if I got it correctly, your question, so it's meaning like what's happening, what is affecting. There we use just a centralized approach, so just other meta heuristic and so on without having this schedule, this distributed framework. But the idea is that here you can even embed some knowledge in each one of the agent, and then you can have some kind of better search when you want to do this kind of rescheduling part. I don't know if it makes it clear. I've completely answered your question.
No. I was maybe more thinking how it's kind of visible in the current experiment, or these kind of effects, what's going on or whatever.
In this one?
Yeah.
No, in this one, no. It's just like there are some functionality about rescheduling that I mentioned before, but it was just to create a kind of, imagine like this. We have this search space that is really huge. You want to simulate the rescheduling as a process to guide the search, nothing more. Then you can also deploy this in the plant, like I can have another feature that can be useful in the production, so in the monitoring part.
Okay, thank you.
Thank you.
We have time for more questions. Anyone?
So throughout the conference, we've been hearing a lot about constraint programming and its power compared to MIP. Can you speculate on whether you think constraint programming techniques would help?
Yeah,
in this
really interesting question. The problem in this case was that we didn't create the first benchmark, and the initial benchmark, it's about floating point value, so for the decision variable. So you can have a constraint programming approach, but then you have to do the grounding, so the discretization of all the problem. And this will we try in some way, but when you map back to the real undiscretized solution, you have a lack of accuracy of the solution. And then at the same time, takes even more time to find the solution rather than this approach, so to the same quality. But thank you so much.
Let's thank the speaker again.